Assalamu alaikum students. Article for today is galvanometer, and galvanometer is a device that is used to detect and measure the current. It detects a very small amount of current and also measures the current as well. And the principle upon which this galvanometer works is when a current carrying loop is placed in a magnetic field, it experiences a torque. How this torque is experienced by this current carrying loop, it has been explained in the previous lecture, that how the forces F1 and F2 are generated in the opposite direction, and a couple produced, and ultimately the this particular coil starts rotating. I'm not going to discuss that. Moving ahead towards the construction of galvanometer. So the first thing in the construction, that we need a radial magnetic field, right? So what is the purpose of the radial magnetic field? um, Radial magnetic, what is basically radial magnetic field? To understand that thing, I will draw a figure later on, but here I am just going to draw the magnetic field, right? So this is the magnetic field which I have taken, right? And in that magnetic field I am going to place a soft iron core, right? This is basically a cylinder made up of strong soft iron core, right? And upon this soft iron core cylinder, I am going to put a frame, right? This is the frame made up of aluminium, just like this. So this is the frame which has been in between this frame, the cylinder has been placed, right? So the cylinder is basically in the center, and over that cylinder we have placed a frame that is made up of aluminium, and on this aluminium frame we are going to wrap our wire in the form of different loops like this, right? So that's how the wire has been given. A lot of coils have been made from a single wire, and that's how it is wrapped over the aluminium frame. Now moving towards the next thing that we have provided here is the current leads, and before that current lead we are having here the hair clips, or you can say hair springs, and this is going to lead towards the current supply. And there is another current supply, and this particular this is definitely that would be the current supply or in this case. So here we have discussed all of the construction. That first we have drawn the magnetic field perpendicular in the perpendicular direction to the coil. Then the soft iron core cylinder. Why we are placing the soft iron core cylinder? Because this soft iron core cylinder is going to enhance the magnetic field, right? As we know that inside this cylinder there would be no electric field, so its purpose would only be to enhance the magnetic field. And then a coil is wrapped around the aluminium frame. Why we need an aluminium frame? Because to give a support to that coil, right? If frame is not there, there would be no support for that coil, right? So because of this thing, aluminium frame has been made. Then comes this hair springs. What is the purpose of hair springs? These hair springs will help wire not to break when the torque effect or this particular coil is going to be rotated. So if the wire would be the straight one, that wire would be easily broken. And but in this condition, if we are having the spring over here, that wire is not going to be broken, right? Now moving towards the current leads, these two then the wire that is the coil, and then this and the other side of the coil, they are have been connected to some battery source or so on. Now talking about the radial magnetic field, what is the purpose of radial magnetic field? How can we create it? So the radial magnetic field could be like this. If I draw a vector, sorry, if I draw the magnetic, so here you can see I have drawn this radial magnetic field. This magnetic field, the direction of this magnetic field is along the radius. Now if I draw the direction of this magnetic field along the radius, I can draw it like this. Inside this particular current carrying loop, it would be like this. Now you see that these field lines are going to intersect at a particular point, but we have read that electric field lines and magnetic field lines, they do not cut each other at any point. So how this is going to be resolved? So here we see that these lines are not going to intersect each other, rather the direction of magnetic field would be like this. And now here you can see, if this is the direction of magnetic field would be like this, then in only this circumstance we observe that there would be no line that are intersecting each other. So I think you have understood this concept, so I'm going to remove this these lines from the center. So here you can see that this is the radial magnetic field, and cylinder is shown, and now the current carrying coil, it would be like this, right? So this is the direction of current carrying coil. You see that the direction of this coil is along the direction of the magnetic field. If I change now, if the coil gets torque, it experiences a torque, it will definitely turn. When it turns, suppose the next direction it achieves, it could be like this, right? So in this case, again we see that the direction of this particular coil is along with the direction of magnetic field. If the direction of coil is to be like this, on this point the direction of the field lines and the coil is again going to be parallel. So here we see that in all the cases, direction of L and the direction of magnetic field is same. So here here is the reason that radial magnetic field is provided, so that at every point force becomes force is going to be produced at different points, like at this point and at this point, right? So on different points, the force is going to be experienced, and ultimately what is going to happen, that torque will be generated. So this was the story behind choosing a radial magnetic field. I think I have covered all the construction. Now moving towards the working. So first we have noticed that torque is going to be produced in this coil, having a magnitude equals to tau equals to BINA, that is bina cos theta. In your book it has been mentioned as bina cos alpha. You can also write bina cos alpha, or alpha is replaced by theta as well. So I'm going to use the equation from the torque article. So the same equation goes on, tau equals to bina cos theta. So this is the torque produced in this coil, and how it is produced, again the same thing. Force would, in this side it would be inward, it on this side it would be the outward force, and ultimately it will produce a twist, or you can say it will start rotating and torque will be generated. Now there was hairsprings used on the bottom side of the coil. So what is the purpose of that? Once the coil starts rotating, it will definitely produces a torque, and this hairspring, it is going to be tightened, right? As soon as it becomes tightened, then what is going to happen, it will be restored, and it will come back to its original position. So when it is restored, the torque which acts to restore the original condition of the coil is basically known as the restoring torque. So torque, what is torque? Torque is basically generated according to this figure which I have drawn. The restoring torque, how it would act, this restoring torque will act in such a direction that its direction would be like this. It would act opposite to the direction of the torque produced. So we can say, suppose if the torque has been produced in the anti-clockwise direction, if the torque has been produced in the anti-clockwise direction, then the restoring torque would be in the clockwise direction, right? So that's how we say that the direction of torque and restoring torque are definitely going to be opposite to each other. So what is the formula for restoring torque? This restoring torque would be having a value equals to c theta, right? This restoring torque, it is having a value that is equal to c theta. Now what is meant by this c theta? We know that C is basically the restoring torque per unit twist, right? What does that mean? That means when there is there's coming a condition that the variation in that particular coil is going to be theta, like suppose it is 1 degree, then the torque would be generated, suppose 1 newton meter. So accordingly, if the theta is like 2 degree, then this torque produced would be in the same condition that it would be 2 newton per newton meter. So we see that this restoring torque is basically depending upon theta. C, what is C? C is basically a constant, and this constant is known as the restoring torque per unit twist, right? uh, per unit twist, how much torque is produced, so that is basically restoring torque. So that is basically C. Now we are going to observe that when the coil is in equilibrium, then this particular deflecting torque, which is deflecting torque or the simply torque, this is equal to the restoring torque. Obviously on the equilibrium condition, both torques would be equal to each other. So in that condition, at equilibrium, what is going to happen, right? So in terms of equilibrium condition, I am going to write this bina. You can remember it through this name, that is bina cos theta. Obviously this force is going to be making an angle of 90 degree with the magnetic force. In that condition, I'm going to discuss the maximum torque case. So bina equals to, in that condition I'm going to write theta equals to 0 degree, and we get the maximum torque to be BINA. So BINA, that is the maximum torque, is equal to C theta, which is the restoring torque. So at equilibrium, deflecting torque and the restoring torque both are equal to each other. And in this case, we observe that if I want to get the value of I from here, we observe that C over the factors B, A, and N, this thing, into theta, right? So from here we observe that C was initially taken as constant. That was it was a restoring torque per unit twist. B is the magnetic field, which is kept constant. A, that is the surface area of the coil, again constant. And that is the number of the loops, so again it is constant. So these are basically constants, and theta is separately written. So I is going to be directly proportional to theta, since constant and equal sign has been replaced by proportionality sign. So here we observe that I is basically directly proportional to theta. Now, if I changes a little bit, there is going to be a deflection. So for that purpose, we have attached an indicator or a needle over this galvanometer, and this needle rotates or moves as the current changes, right? So this formula is very important. This relation is very important, and this is the working basis of galvanometer, on which it measures or detects the current. Now talking about galvanometer sensitivity, we know that if I want that a very small amount of current should be detected by this galvanometer, what should be the steps to be followed? Firstly, this C, that is the restoring torque per unit twist, it is directly proportional to I. So the value of C should be, if I increase the value of C, I would definitely increase, right? Number two, if I decrease the value of B, because it is inversely proportional to I, so if I decrease the value of B, I would increase. If I decrease the value of a cross section area, again I would increase. And lastly, if I decrease the value of n, obviously I would increase. So overall the effect would be like this whole C over BAN, the value of this will be like small. If this C over BAN will be made small, ultimately what is going to happen, that if this value is very small, then theta would increase, since they are inversely proportional to each other, so theta would increase. So now if I say, and this C over BAN, it is directly proportional to I. Now we notice that if this constant C over BAN, it is made smaller and smaller, what is going to happen, that I would decrease, right? That means a very small amount of current, right? Now if a very small amount of current passes through this galvanometer, what is going to happen, we are going to get theta very large, right? So for a very small current, we are going to receive a large deflection, and that's how this describes the sensitivity of a galvanometer. Consider that if suppose 1 microampere current passes through the galvanometer and a deflection comes out to be of 1 degree, then it is one first case. Now the second case is if again simply zero point 0.1 amperes of current passes through the galvanometer, another galvanometer, and the deflection observed to be 4 degree. So which galvanometer is considered to be more sensitive? Obviously that 4 degree would be considered as more sensitive. Why? Because when a small amount of current has been passed, it is providing a greater deflection, right? So that's how this galvanometer instrument is considered to be very sensitive. And usually the main problem with the galvanometer is that it is so sensitive that sometimes with a very small amount of current it gives a full scale deflection. And due to this problem, we cannot measure the values of current accurately, right? So if it is giving on point, like suppose if it is giving if it has been given a value of zero point 0.5 microamperes, and it is giving a full scale deflection on that, and I'm also providing zero point 0.1 microamperes of current, uh, or you can say like 1 amperes of current, suppose 1 microampere current, then what is going to happen, it is again going to give you the full scale deflection. If I'm going to pass 2 microamperes of current, it is again showing the full scale deflection. So what does this is the major drawback of galvanometer, that it is a very sensitive instrument, that whenever a small amount of current is going to pass, it gives a large scale deflection, and because of that, measurement is generally not possible. So for because of this drawback, m-meter has been devised. And what is m-meter, we will definitely discuss in the next lectures. So coming back to the article now, what are we having? We are having the two types of galvanometer, which are Lampscale method. In this method, which is known as the Lampscale method, you can see that we are having a lamp over here, and there is also a scale over here, right? And there is an arrangement in the front of that. What it is that we have placed the same configuration. There is a permanent magnet, there is a coil, that is a fixed, sorry, there is a fixed core, then there is a moving coil, and so on. Here we are having a little thing that is known as the mirror, right? This is the mirror. And what mirror is going to do, as this lamp is going to throw some light on this mirror, uh, this mirror would definitely reflect that light. So what is going to happen that when this lamp produces light and it falls on this mirror, it definitely show that particular light spot onto the scale, right? Suppose it is lying in the center. Now if it is lying in the center, that means the coil is not moving. When the coil is not moving, that means no current is passing through the coil. So we say that when the mirror is showing on the scale that the spot is in right in the center, that is on 0 degree, that is on 0, then what is going to happen? There is no current passing through the coil. Now as soon as the current is passing through the coil, and definitely when the current will start flowing, definitely torque will be experienced, the coil starts moving. And when this coil starts moving, what is going to happen? The attached mirror is also going to move. Now accordingly, lamp is again throwing light on the mirror, but now the direction of mirror has been changed. Now this light falls on this mirror, and now the reflection would occur at some different point, right? Now at this deflection, if it occurs at some different point, so we will definitely measure that on the scale, and we say that from the center, like if this is the center, and at this condition, and we notice that this scale, the spot is now here at this particular point. So we have attached a needle with the coil, and ultimately we notice that the needle will move towards that point. So we notice that how many degrees have been shifted by this particular on the scale, and we notice that in this condition, if suppose 5 amperes of current have been passed through this galvanometer, then how much deflection has been observed? Suppose the deflection which is observed is of 5 degree, so that means if there is 1 amperes of current, or you can say 1 microampere current is passing through this particular galvanometer, then the theta observed is to be 1 degree, and so on. Suppose if 5 microamperes current has been passed, so that means 5 degree of the deflection is observed. So that's how the reading which you observe on the scale has been then calibrated to get the value of the current. So that's how this lamp scale arrangement works. Now coming towards the next type, which is a pivoted coil galvanometer. And this pivoted coil galvanometer, how does it look like? Again the same thing. There is only one difference between both of them, that here we have here we have using here we are using the jewels, right? So there are jewel springs have been used, as indicated like this. So these are the two jewel bearings, or you can say the jewel springs are used, and the rest of the arrangement is the same. We are having a scale shown with the yellow scale, as you can see the same over here, and the same stuff, permanent magnet, and the armature, or you can say the frame on which the coil has been mounted, or you can say wrapped, and the two current leads have been connected with the help of these hairsprings, or you can say the jewel bearings. What sort of difference the both of these types are having? The major difference between both of them is lamp scale arrangement is not a fixed one, right? So when it is not a fixed arrangement, what is going to happen that after measuring the value of current, the because of the torque and then the restoring torque, this coil is going to be rotated continuously until it comes back to rest, right? So because of that, the needle which is attached, it is going to be deflected, or you can say it is going to shiver on a point, on from one point to another point, right? So it is not, definitely it is not coming to rest, because the coil inside the galvanometer is not at rest, right? So it will definitely shiver on its part, and it will be time consuming to wait for the needle to come to the rest position, and gives you the accurate measurement of the current. So this is the major drawback in lamp scale arrangement. So we use pivoted type galvanometers, in which uh, the current leads, these are fixed, right? So if these are fixed, there is going to be a no or a very very little shivering of this needle, and it will come back to its original position immediately, and it is not then time consuming to, or you can say we do not need to wait long for the galvanometer's needle to come to rest, and so that we can measure the value. So this is the major difference between pivoted galvanometer, that in that the current leads are fixed, and in the lamp scale arrangement the current leads are not fixed. So there is going to be a little problem, time consuming method would be observed in the lamp scale arrangement. These are some real figures related to lamp scale arrangement. This is the lamp scale arrangement shown, which in which from which we are observing that there is a linear scale, and we are having a lamp in front of it, and on the left side we see that black and white figure, in which we observe that there is a scale which is somehow semicircular, and there is a magnet, that is the U-shaped magnet, and then the radial magnetic field, and armature, and so on. So this is the arrangement, these are the real pictures of pivoted type galvanometers and lamp scale arrangement. uh, the galvanometer which we generally see is just like this. This is the general galvanometer which we usually use in our labs, and in this you can see there is a scale, and on which in the center there is 0, and on the right side there are positive values, and on the left side there are negative values. Obviously theta would definitely be, the coil can be rotated in the clockwise, like if talk about the deflecting torque, or you can say the direction of current. So because if the direction of current is in the clockwise direction, definitely theta is going to be negative, and if the direction of current is going to be in the anti-clockwise direction, then theta is going to be positive. This happens because if we change the terminals, the two terminals which we use is basically the negative one, that is the black one, and the G1 terminal. Usually these two terminals we usually use, and when we change the polarities, like if I'm going to connect the negative terminal with the positive terminal, of the battery or whatever circuit, if I'm connecting that to that, then what is going to happen if I'm changing the polarity, like positive to negative connection and negative to positive connection? In that case, we get the values in the negative side, like towards the left side. And if the connections are made correct, that is positive to positive and negative to negative, then in that condition we get the positive deflection, that is towards the right side. That's all for today's article. Thank you so much. Allah Hafiz.